So for the time being, just wipe your memory clean of that test. I'll hopefully look at it and get it graded over the weekend, or hopefully back to you guys by Tuesday. Chapter 8.1, we're going to skip 8.2 after all because time. So we're going to look at 8.1 and 8.7, and that's it from Chapter 8. So we're very close to done. We have like one small quiz left, and then we're done the curriculum. So,
Can you let the miss off?
all right, thank you. So just shush. So 8.1 is a review of all the integration techniques we've ever seen. It's nothing new. It's just a review of all of these. 8.2 is a new integration technique that is not on the AP exam. I wanted to show it to you guys, but that can wait. I'll just wait until after the AP exam. That'll be like a day or two, just so you've seen it before you go into college. 8.3, 4, 5, and 6 are other integration techniques and are also not on the AP exam for us. They're on BC. And those don't show up in Calc 1 probably anywhere in college, whereas the 8.2 stuff probably will in some colleges, which is why I want to show it to you guys just in case you go to a college where it's in Calc 1. 8.7 is in our curriculum, and that's cycling back to the limits, where we use differentiation to make us be able to take limits more easily. So we have to look at 8.1 and 8.7 because that's what's going to be on our AP exam. 8.2 through 8.6, for our purposes, is irrelevant with regards to the AP exam. So 8.1 is just reviewing all the integration we've ever done. So running through a bunch of examples. We've looked at your backwards power rule. So we've been doing that a ton recently. What's the integral of, say, x squared dx? 1/3 x cubed plus c. Generally speaking, what's the integral of x to the n dx? 1 over n plus 1, and then x to the n plus 1, because you divide by the new exponent, and then if you're doing an indefinite integral, plus. All right, so that's backwards power. U substitutions, it's been a while since we did those, so we're going to see all these other things coming back. So a U substitution, those can show up in a lot of different ways, but for example, let's kind of combine a U substitution with an exponential function integration. Say you have 2x e to the 3x squared dx. What would be a good choice of U? 3x squared, and then du would be 6x dx. And then what do you see is missing from here and your du versus dx? A factor of 3. So we need another factor of 3 here. So to make that happen, multiply by 3 inside, and then to keep things balanced, what do we also do? Yeah. Divide by 3 or multiply by 1/3 on the outside. And you're allowed to do that with only constants. You're never allowed to do that with an x. If you look at this, it's like, oh, I need another factor of x. You're not allowed to multiply by x and then divide by x on the outside. You can multiply and divide by x on the inside, and sometimes that's useful, but not always. So now you look at this and say, all right, this is 6x dx. That turns into du. E to the 3x squared is e to the u. And you have a 1/3 just sitting out front. And then what's the integral of e to the u du? E to the u. Plus c, 1/3 out front. And then what is e to the u? The same as e to the 3x squared plus c. So that's what that would look like. So that's a combination of a u substitution with integration of an exponential function. We can do that also with all sorts of other things, like general fractions. We can do that with radical functions. We can do that with trig functions. U substitutions are useful all over the place. Let's review just our trig antiderivatives. This is 3. This is where things get a little tougher. What's the integral of cosine x dx? Sine x. Is it positive or negative sign? Positive. But what's the derivative of sine? Positive cosine. Yeah. What's the integral of sine x dx? That's negative cosine x plus c. All right. Other trig antiderivatives. Integral of secant squared x dx is tangent. And therefore, the integral of cosecant squared x dx is negative cotangent. Integral of secant x tangent x dx is secant. Yeah. It's in your notes somewhere. What we're doing is we're gathering all this together into one place. Integral of cosecant x cotangent x is negative cosecant x. And I'm organizing it out like this to kind of see positive trig integrals and negative trig integrals. And these, so far, are the nice ones. And then we have the not nice ones. So, integral of tangent.
No, isn't that is that the 1 over the 1 over?
It's the natural log of ugly. So, I think it's a secant.
Oh, it is secant x plus something.
Yeah, I think it's
tangent x.
secant x plus tangent x in
Okay,
there.
yeah. It's just in the LX. Yeah.
Now,
Okay.
I'm not 100% sure on that, so before I lie to you guys, as I've done in the past,
I'm 90.
we should probably double check.
I think
So, if we did the derivative of this guy with chain rule, what's the derivative of secant? What's the derivative of secant?
secant x tangent x.
Secant x tangent x. What's the derivative of tangent? Secant squared x. And then that would go over secant x plus tangent x. Uh-oh, I think I may have lied to you. What can you factor out here? A secant x, and what's left over? Tangent x plus secant x, so what cancels out? Tangent x plus secant x, tangent x plus secant x on the top and bottom, and you're left with secant x. So what is this actually the derivative?
Secant x.
This is actually secant x.
That's what I thought because it's easier to memorize because
So good thing we're reviewing this and that we checked. No, that's cosecant.
because the way you remember secant x is secant x times tangent x and then secant x plus tangent x. They're like both.
So, using that rule, what's the integral of cosecant x dx? Before the ln? Negative ln of cosecant x plus cotangent x plus c. So, same thing, but negative, and using the co-functions of what you had over there. All right, the other ugly one is the integral of tangent. I literally cannot find it.
I'm determined to find it in my notes.
So the integral of tangent x dx, see, when would this have been? Probably in like 4.5.
I found it.
Okay.
Negative ln of the absolute value of cosine x.
All right.
I'm sorry. That was tangent.
Yeah. So good goal. And therefore, the integral of cotangent x dx is same thing, sine, and is it a positive or negative natural log? Positive. So that is all your trig antiderivatives.
How nice.
Delightful. Top ones, top three, not so bad. The bottom ones, they don't play nice. So these are ones you just gotta memorize. Flashcard these. So take the time. If you made flashcards before, great. Review them every night for like 2 minutes, 5 minutes, like 5 minutes a day. Flashcards with all the formulas and all the things you need to memorize and all your theorems is worthwhile. And making flashcards a second time can't hurt. The more you write it down, the more it gets from your hand into the brain. Now, inverse trig functions.
Oh, these are the ones with the 1 over.
Yeah.
Okay.
So,
I
That was
This is very
3, so then this is 4. So inverse trig functions. This was chapter 5.7, I think. Yeah. So the integral of
1 over root a squared minus b squared
a squared minus u squared du.
is arc sine u over a plus c. That's a good question.
Right? Say again? So
5.7.
this was chapter 5.7. These things were kind of jumbled throughout chapters 2 through, I'm sorry, 4.
That's for something. That's five. That's
Yeah,
fine.
this was throughout chapters 2 through 4. This was chapter 5.7.
That's 5.2.
5.2.
That's what I have it written.
5.6. 5.6 and 7. I think 6 was derivatives and 7 was integrals.
Oh, this is.
Yeah. So integral of, I think it's 1 over a squared plus u squared du
1 over a arc tan u over a.
is 1 over a, where a is just some number, times the arctangent of u over a plus c. And then the integral of 1 over, I believe it's u, times the square root of u squared minus a squared du. Is that correct? Of
1 over a
1 over a
arc secant
arcsecant of,
absolute value of u
oh, absolute value of u
Yeah.
over a plus c. So I knew that one of these had an absolute value of u. I couldn't remember which one. So these things again, you just gotta know. Good news is they don't show up very often.
Why?
Why? Because they're not very common. So these things are fairly rare, so they don't show up very often. On the down, so like if you see it on a multiple choice, what you really need to know is, hey, what is this pattern? If I see that pattern, what does it map out to? And recognize, oh, that's the arcsine pattern, that's the arctangent pattern, that's the arcsecant pattern. Recognize the pattern when you see it. A lot of these are just pattern recognition. And the way to recognize patterns is to see the same pattern again and again and again in different contexts, and then you start to kind of remember it better. So flashcards, again, learning the pattern in the first place so you know what you're looking for, flashcards can help with that. And then the other integration techniques we've done are exponential and log, where like 1 over x becomes the natural log of x, stuff like that. And then Riemann sums, which is like the left hand, that's like if you have a table of values. Yeah, the rectangle. So Riemann sums, the last thing is like left hand or right hand or midpoint when you're working with a graph or a table.
And the trapezoid one.
Yeah, or a trapezoid. Trapezoid is just the average of left and right. So, or trapezoid. So, if I gave you like a table, let's say here's x and here's f of x, and say like 0, 3, 5, 10, and this is like negative 3, 7, 8, 11, and I wanted the integral from 0 to 10 of f of x dx using a right-hand sum. A right-hand Riemann sum. This is just base times height a bunch of times, and if you're using the right edge of each rectangle, for this first interval, what's the width of the rectangle? Nope. 3, from 0 to 3. There's your base. And then the height at the right edge is 7. Because f of x is your y coordinate, that's your height. That's y. So this is delta x is base of each rectangle, and then the y coordinate is the height. And which y did you use? The right one, because you're doing a right-hand sum. So then for the next rectangle, what's the base? 2, and the height is, and then the next one, the width is, and the height is 11. So you use the delta x, but you use the y value. So the y value is the height, the base is the delta x. So then you would just multiply and add those up. And if you did the left-hand sum, same bases, but then you're using the left edge of each interval for the height, so -3, +7, +8, and you don't use the 11. And if you wanted the trapezoid, you would take the right and the left and average. And with this sort of thing, you cannot do midpoint because you don't have information. You don't know what F1.5 is. So that's Riemann sum. So that's all the integration techniques in a nutshell. And then within each nutshell, we can go like into real, like, get in the weeds. And that's going to be what 8.1. So this is just kind of introduction to our review of all integration techniques. Yes. Depends on the specific situation. So midpoint versus trapezoid is kind of a toss-up as to who's more accurate. They're both more accurate than left and right pretty much all the time. And then left and right, you can tell overestimate or underestimate based on the curve increasing or decreasing. So let's assume, look at these f of x values. Does it look like f of x are increasing or decreasing? Looks like it's always increasing. So let's assume that between 0 and 3, and between 3 and 5, and between 5 and 10, that pattern continues. So let's assume f of x is always increasing, because that's what it looks like. Is the right-hand sum an overestimate or an underestimate? Overestimate. So increasing means right hand is an overestimate and left hand is underestimate. Decreasing switches that. Pass, yeah. And if it's up and down, if it's increasing and decreasing over the interval, then you don't really know left or right who's increased, whether it's overestimate or underestimate. All right, Joanna. There is a formula, but usually I think it's easier to just kind of do left and right and average than to work through the formula. What room are you going to? 24. All right. So what we're going to do now is just kind of just go through a bunch of examples. And for each example, what we're doing is everything's kind of getting jumbled together. And we have to look at these example and kind of analyze, okay, for this example, which pattern is applicable here? Is it a U substitution problem, or is it an inverse trig situation? Is it something sneaky that we just haven't ever looked at and we just don't know how to do it yet? Because we can throw that at you too. So that's going to be our goal now for 8.1. Yes, ma'am. Okay. Honestly, that's probably this is as good a time as any for whiteboards. So yes.
Genius. Thank you. That
I like that.
That's
Honestly, that doesn't deserve a word.
If Sam says so, then it must be so. Here you go. 15 minutes. That's just a lot of time. Thank you.
No, that's
You are such a big.
You forgot.
Holy
Did
cow.
I forget?
no, you didn't forget.
You
Did
should
you
give
give us extra? I don't know.
You were trying to grab it from me, so
Because you already know what you
I turned it and
Wait.
What?
I didn't mean it. I don't like that. You can have a second
Hey, did
one.
you pass out marker?
Yeah.
Can I have a second marker?
Nice attempt. Thank you. You're my receiver and I'm the quarterback. I'm yelling at you when you come back to the huddle. That was pathetic. You really tried your hardest.
I know. I'm really small.
It's like watching girls in gym class play volleyball.
No.
All right, integral of 4 over x squared plus 9. dx.
I know.
She gave me a bad
They're all bad.
I'm just kidding, I'm kidding, I don't want to.
Can I have one? My cat's
My catch.
not in my lap.
Yeah, that's what laps are for.
Oh wait.
I forget all of this.
There's that.
Oh, wait.
Oh, I didn't. Wait, when did it come?
So here you're thinking, is it a U substitution problem, or is it a divide out the fraction problem, or is it a fit it to a inverse trig pattern? Yes. Must be.
Oh, it's one of those. Oh, you.
Oh, what?
What y'all say?
Yes.
What does the four do?
It's just a multiplier. You can pull it out if you want to.
When it goes in the
I got it.
Yeah.
I got it.
So that's going to be the inside of the inverse trig function. You got to figure out what's the inverse trig function around it.
Wait, so we're figuring out which one of those three is?
Not 1 over x, 1 over a. In this case, a is 3.
Yeah, but is it
No, A is X.
Adding is commutative. So a is a constant. U is
why
variable.
did you say that?
So
Yeah.
those are yes. Yeah. So it'd be there you go. Yeah. So the 4 is a multiplier, so that multiplies to the pattern then, and inside is going to be a x over 3.
Yeah.
All right. Cool. So here, if you fit this to your pattern, you should see, hey, the numerator is just a constant. You can pull the constant out, and it's like dx over x squared plus 9. That fits our arctangent pattern pretty well. If you get u be your x and a be your 9, then u is x and a is 3, because a squared is 9. And then du equals dx directly. So that's nice. And then we just have this extra 4, just pull it out. So when you go to integrate then, this is the arctangent pattern. You have 4 times 1 over a is 1/3, times the arctangent of u over a is x thirds, plus c, that's an x. And then multiply by the 4, you have 4/3 arctangent of x thirds. For all your arctangent, arcsine, arcsecant patterns, x has to be your u stuff. Like your variable can't be a. A has to be the constant part. All right, next one, similar. Integral of 4x over x squared plus 9 dx. So same thing, but now it's a 4x up top instead of just a 4.
Oh, that's not you.
So
Oh, yeah.
Thank you.
that is u substitution. Yes, please do u substitution.
Well, you
there.
said similar to the other ones.
So it's similar in how it looks.
Oh.
Integrals that look similar might require extremely different approaches.
Awesome. Because I was gonna do you substitution, and I was like, it's gonna be something.
Oh,
Wait,
that was
what?
fast. Let me think.
No.
You might be right.
No, you have to put it 2 out.
Why? Oh,
So,
2x.
2 times 2x.
Yeah.
Yeah.
Good stuff.
That's u over that. The u, that's a 2 times the natural log of that. Let me see it again. Yeah. Good stuff. That's good. Natural log of that thing. You did natural log, so it's natural log of u, not natural log of du.
Yeah.
Yes. Yes.
Okay.
There you
What if you
go. But it's an easy fix.
What if you write? I got
Wait,
And then don't forget, it's not about you.
So are you not allowed to keep it in terms if it says
Good.
what
if you're,
Why have u equals that?
we'll always want you to put it back in terms of x unless it's a definite integral plus c. If it's a definite integral and you have bounds, you can convert them into terms of u and then do that. But if it's an indefinite integral like this,
Go back to that.
always get back into terms of x. All right, yeah, so that was a u substitution. U is x squared plus 9. Du is 2x dx. If you look up here at the 4x, you would see, hey, that's too big by a factor of 2. So you can turn this into 2x times 2 and pull that extra factor of 2 out. And then that's du over u. So we would have 2 times the integral of 1 over u du is 2 times the natural log of absolute value of u plus c, and then convert that back into terms of x. Yes, Michaela.
I had this question before.
Go for it.
Well, we, okay, so we put this out front, but technically we're putting like the 1/2 on the inside, but the 2 is on the denominator.
So you could think of this as we want to make this a 2x, right? So we have 4x. To make it a 2, we can times by a half
But if you're multiplying by,
and multiply by 2.
like if you're multiplying the whole thing by a half, it goes on the bottom.
You can do either or. You can multiply the whole thing by a half, and then you have an extra factor of 2 down here, and 4 divided by 2 cancels.
Okay.
Or you can multiply just in the numerator, and same thing. So yeah, you can think of this as to make this a 4x into a 2x, multiply by a half and times by 2 on the outside. Just like over there, somewhere we multiplied by 2 and on by a half on the outside. All right. No, this is I'm not sure what these are. Avocados or kiwis or loogies of somebody who's sick. I don't know.
That's the word. Can you come to school ready?
No, because I don't have one. And I don't want the inevitable comparisons to our principal.
If we,
So-
oh my gosh,
If we
can
all
you
chip
meet
in.
Simone for a day? Can you like dress up as a kilo and get the nails?
You and Simone should explain
And then like really dumb
Please.
that
Please.
Mr. Egger, all pink for Wednesday work.
No,
Yes.
no.
Yes.
Next one.
No. He needs like a little. We're not moving longer than this.
No one do the work until you come on.
Right on the board.
That's right there.
Pink ones.
All right. So again, it looks very similar to the ones we've done before. Approach is going to be very different. This is Bethlehem's favorite
Oh, this
method.
is illegal.
No, I already started. What?
Nah.
That
It's the
looks like
same-
long division.
It's a long division problem, but Bethlehem's going to try to force U substitution to work. And she'll probably find a way to succeed because she's good at that. But you can do long division. That's what I would do.
The numerator, it's the numerator and then the
Numerator divided by
Oh,
denominator.
never mind.
Oh my god.
So-
Every time I go to do division, I write it as a square root.
Damn, I forget this.
So this is what you would do for if the top degree is as big as or greater than the bottom degree. Yeah.
I forget all this.
Wait, hold on. I put out the 4 before I started. Is that fine?
Yeah, that's fine. And then at the very end, you just multiply by 4 to your final integral.
Would this be the proper cutout?
Let's see. U squared, so U minus 9 square root is x. And du equals 2x. Yeah, that's
Okay,
good.
that's the okay.
I don't know. I haven't worked this out. So that goes over there. 4 times. Well, and then 4x squared plus.
So you do this by the whole thing.
So this goes into the first term 4 times. Then I take the 4, multiply to the whole outside,
And then you subtract.
and then you subtract, and you get negative 36 as your remainder. So this is the same as the integral of 4 minus 36 over x squared plus 9. And then you have 2 different integrals to do. So the integral of 4x, and the integral of 36.
Wait, I'm really.
Oh. Oh, because that's
Alright.
the remainder. So it's the remainder over the top.
Yeah, remainder over the divisor.
Why you subtract?
Because it's a negative.
So then how do you do the remainder?
All right, so have a seat, please. Thanks, because you're blocking Javier. So divide the fraction. If the top is greater or the same as the bottom in terms of degree, divide out the fraction. And the way you long divide out the fraction is top inside divided by the outside, bottom. X squared is into 4x squared, so you take the first term into the first term, see what you get. Multiply that to the whole outside, see what goes underneath, subtract. And then in this case, you're done. That's your quotient, 4. That's your remainder. It goes over the divisor, and now you integrate this. So you integrate the 4. That works nice. And then you integrate the 36 over x squared plus 9 dx.
How do you?
And that is back to
That, John.
arctangent.
I hate this.
Oh,
U
that's-
is x and a is 3, and you're multiplying by 36. So you'd have 4x minus 36 over a is 3 times the arctangent of u over a is x over 3 plus c, and then that's 12, obviously. So you have 4x minus 12 arctangent of x thirds plus c. So that one's obviously the yuckiest that we looked at. If we had 4x to the third or 4x to the fourth and so on, then we would still use this method, but we would have more terms up as our quotient as we have bigger exponents to deal with. I think is a good chance of the other ones, for sure. This one, I think, is a coin flip. I think the first one that we did was just pure arctangent. I think that is definitely fair game for like a multiple choice. And if you recognize your pattern, it's like, because the wrong options will like not probably even involve arctangent. They'll use some other trig, arctrig, inverse trig function, or they'll be as though you did a U substitution instead of trying to fit it to an inverse trig pattern. So if you know your inverse trig patterns, that one should be pretty easy as a multiple choice question. The U substitution is fair game for sure. This one, it's fair game, but I'd say it's probably more of a coin flip as it shows up or not.
How? Okay, so you know how this,
Mhm.
if this was squared, right? You just multiply the 2 by the top right, right?